according to Popper, and I entirely follow him in this matter, all knowledge, not just scientific knowledge, begins with a problem and then continues with conjectures. Existing theories are existing conjectures. So you could say it starts with existing conjectures, but we don't actually do anything with those until a problem arises. A problem is a prima facie conflict between our ideas, which could be as simple as we can't get the experiment to work. Okay, maybe it wasn't plugged in. Maybe we got a low quality transistor in there. Or maybe the laws of physics aren't what we think they are. Contrary to what the prevailing theory would say, that's not the first result. That's pretty much the last result. We don't do an experiment hoping to get a violation of the laws of physics. That never happens, absolutely never happens. The only time we ever discover a violation of the laws of physics is if we already have, at least in rudimentary form, a rival theory. If we have more than one theory, or if there's one way of tweaking the theory or another way of tweaking the theory, something has got to be in conflict, because if we only have one theory, if we really only have one theory, then what we will naturally do, and what is absolutely the right thing to do, is to write off the apparent violation of the theory as an error. It could be an error, it could be a fraud, it could be a misconception, it could be bad apparatus. We're going to try everything, and only like halfway along that everything will somebody ever say, well, maybe the laws of physics aren't what we think they are. And in fact, the whole process of doing scientific experiments, especially in physics, is debugging, just like that's what computer program is all about. You have this apparatus, you switch it on, of course it doesn't work. You're not God Almighty. You haven't set up this great big complicated thing in the lab and it works first time. No, it probably doesn't even work until the 50th time, And as it doesn't work, the same process happens. You have conjecture, you have a problem, it's not working, or it is working, but it's indicating the wrong value, or everything's off the scale, or everything's at zero, or whatever. And first thing you do is you form conjectures. Maybe the instrument isn't the right one. All the things I mentioned that could go wrong. And sometimes you have to be very clever about what could have gone wrong. And experimental physics is very difficult. I'm always in awe of experimental physicists when I visit them because of the inordinate effort they have to put in to just getting the apparatus to work. And then, only then, can you test something. And they're not going to think kindly of you if you told them to do an experiment where you already know the answer, where there isn't a rival theory, where everybody knows what the answer is. Sometimes we want to do that because the answer is so weird that we can hardly believe it. That is the prediction of our best theory is so weird. Now, I would classify that as there's a conflict between our best theory and common sense. And common sense is such a strong expectation that the experiment will go one way. And then somebody has come along and said, look, I've calculated what should happen. And it's totally counterintuitive. And then you might say, okay, let's try it. Let's actually try it. Let's put it to nature and see what happens. And there are many examples, including famous examples of people who have done a crucial experiment of testing the best theory against intuition, expecting intuition to win. They do the experiment, they do it very carefully because they want to really pin down that this theory has got to be wrong. And they do the experiment, and it turns out to be that the theory is correct. Sometimes it happens that the theory isn't correct. But the point I'm making is that we start with a problem, we have conjectures, and experiment is pointless unless we have some kind of conflict that we want to resolve.
Quantum physics and multiverse theory, I think, is the remaining one.
Yeah, so those are the two most obviously connected, because the idea that quantum theory is a theory of parallel universes. By the way, it was Schrödinger who really was the first, but he never developed the theory. Everett was the one who developed the theory, introduced the terminology, the details, connected it with other parts of physics, and so on. And then I was sort of mystified why people didn't get this, because to accept the Everett interpretation, so-called interpretation, is simply to accept quantum theory. And you have to go along with the arguments that you just have to do as a physicist. You have to do what you're trained to do and judge these theories by the methods that we're trained to judge them by. And nobody does. So I thought, okay, I'm going to sort this out. So I thought Everett was actually mistaken when he conceded that no experiment could distinguish between his multiverse version of quantum theory and the rather vague nonsense, I would say, that goes under the name of the Copenhagen interpretation. By the way, just a side remark, Copenhagen interpretation is a misnomer. Copenhagen interpretation was founded by Niels Bohr, and he had a sort of idiosyncratic view of how one should view quantum theory. And the thing which was later called the Copenhagen interpretation was actually invented by John von Neumann. And he didn't intend it to be the last word in quantum theory. He intended it to just be a stopgap measure that could be used without bothering with these esoteric questions. So I thought he's wrong about it can't be tested experimentally. I thought of a test, and the test, of course, had to involve, because you always need two theories, it had to involve the existing theory, and the existing theory involved an observer, whatever that is. You know, the consciousness changes the wave function, makes it collapse. So I thought, well, you can't easily do microscopic experiments, quantum experiments, on an actual observer. So I imagined that one day we would have fine enough control over individual, what's now called qubits, quantum mechanical bits, to use quantum mechanical bits in a computer and then run an artificial general intelligence program in that computer. And then it could do an experiment on itself. And it would be very straightforward. If the outcome was one thing, then there are parallel universes. And if the outcome was another thing, then there aren't. I wrote a paper about this, and in order to make it all work and dot the I's and cross the T's, I had to describe this computer as a computer. We would now call it a quantum computer. But this was around about 1977, 78. I did not call it that. I didn't think of it as that. I thought of it as an experiment, a thought experiment that was far from being doable, because you had to have two things, what we would now call a quantum computer and what we would now call an AGI, and the AGI running on the quantum computer. So quantum computers, in a way, came into the world, or rather into the conceptual world, via parallel universes. They can do this experiment. A classical computer couldn't do it. And if it's false, either computational universality is false or quantum theory is false, then the experiment won't work. Yeah, and we don't even any longer try to align humans in the way that people want to align AGIs, namely by physically crippling their thinking. Yes, I don't think we're anywhere near it yet. I'd love to be wrong about that, but I don't think we're anywhere near it. And I think that AI, although it's a wonderful technology, and I think it's going to go a lot further than it is now, AI has nothing to do with AGI. It's a completely different technology, and it is in many ways the opposite of AGI. And the way I always explain this is that with an AGI, or a person, an artificial person, their thinking is unpredictable. We're expecting them to produce ideas that nobody predicted they would produce, and which are good explanations. That's what people can do. And I don't mean necessarily write physics papers or whatever. We do this thing in our everyday lives all the time. You can't live an ordinary human life without creating new good explanations. An AGI would be needed to build a robot that can live in the world as a human. That's Turing's idea with what is mistakenly called the Turing test. Now, why an AI is the opposite to an AGI is that an AGI, as I said, can do anything, whereas an AI can only do the narrow thing that it's supposed to do. Like a better chatbot is one that replies in good English, replies to the question you ask, can look things up for you, doesn't say anything politically incorrect. The better the AGI is, the more constrained its output is. You may not be able to, say what the result of all your constraints must be. It's not constrained in the sense that you prescribe what it is going to say, but you prescribe the rule that what it is going to say must follow, or the rules. So, if it's a chess playing program, then the idea is you must win the game. And making a better one of these means amputating more of the possibilities of what it would otherwise do, like namely lose, or in the case of chatbots, say the wrong thing, or not answer your question, or contradict itself, or whatever. So the art of making a good AI is to limit its possibilities tremendously. You limit them a trillionfold compared with what it could be. There are a trillion ways of being wrong for every way of being right. The same is true of chess playing programs. Whereas the perfect AGI, as it were, would be where you can show by looking at the program and can show mathematically that there is no output that it couldn't produce, including no output at all. So an AGI, like a person, might refuse to answer. It should have that right, by the First Amendment. So you can't have a behavioral test for an AGI because the AGI may not cooperate. It may be right not to cooperate because it may be very right to suspect what you're going to do to it. Do you see that this is not only a different kind of program, it's going to require a different kind of programming because there is no such thing as a specification. We know sort of philosophically what we want the AGI to be, a bit like, parents know philosophically that they want their children to be happy, but they don't want, if they're doing the right thing, they don't want to say, well, my child will never say X, will never utter these words like you do for an AI. You will recognize what it means to be happy once they've done it.
I think fundamental to your worldview and explanation of what humans are is humans create knowledge through creativity. And what you're basically saying is that an AI, the narrow AI, is not allowed to be creative. It has to solve a specific problem. And true creativity means you can hold any idea in your head. It's unbounded. And so it can display any behavior pattern. And until you see that this thing has complete ability to be creative and therefore output any behavior pattern, you haven't created an AGI. You've just created a narrow, constrained automaton.
Exactly.